Okay, folks, let's go ahead and let's pick up where we left off with yesterday. First of all, I hope the video yesterday was a little bit more doable. That I tried to time it so that you can get the video watched and get the work done in time as well, and do the last two problems at the end and submit it. I'm going to continue to try to refine and try to get the timing right so that you don't feel rushed. So bear with me as I try to work this out and work through this. But your input would be helpful too. Just let me know. Comment on what you think about the video, and then I'll make the adjustments. And if I'm going too fast, let me know. Or if I'm going too slow, let me know. I think we're going a little bit slower than I would like, but under the circumstances, we're going to try to get as much done as we can. Okay. So let me know. I come on by after school today. I'll be after school today. I'll be there also on Zoom on our Zoom classroom meeting and ask your questions. Okay. I'm sorry. Today, this afternoon, something came up, and so unfortunately I wasn't able to attend and open up the Zoom classroom. I apologize for that. But I will make up for it. So I will be around tomorrow to take your questions live after school, 3:15 to 4:15. And so let me know. Okay. Um, okay. Well, let's go ahead then, and let's quickly review where we left off with yesterday. Yesterday we were talking about ions, and we were talking about why atoms, at least why they form in terms of the electrons. So we know then that when bonds form, the atoms that come together, they have to become more stable. They have to become more stable as a compound than they are separated. And we saw then yesterday why they could become stable. They become stable by either sharing electrons or giving up and getting electrons, and sharing and giving up and getting enough electrons in order to obtain the electron configuration of a noble gas. We know noble gases are stable, with the exception of helium. We know that they're stable because they have 8 electrons in their valence shell. They have completely filled s's, and they have completely filled p orbitals. Okay? And so what other atoms try to do that are not noble gases is that they try to achieve that noble gas configuration by either sharing electrons in the case of covalent bonds, or giving up or getting electrons, as is the case with ionic bonds. Okay? And so we saw then that when two nonmetals get together, they will share electrons in order to achieve that octet. And when a trans representative metal and a nonmetal get together, they will exchange electrons in order to obtain their octet, with the nonmetals filling up their valence shell so that they can get their octet, and with the representative metals, they will be emptying their valence shell in order to obtain the octet with what is left over. So you want to make sure you keep that in mind as we move forward. Then we saw then that we saw then that the stability then changes the size of the atoms as well. And so with the ions, and we saw then that with the cations, they would be smaller than the neutral version of that atom, and that the anion would be larger than the neutral version. So by removing electrons, we make the atom smaller. By adding electrons, we make the atom larger. And so the size of the atom is going to be dependent on how many electrons it has, okay, initially. Then we saw then that we can also, and then I also reminded you that we can determine atom sizes and ion sizes using the periodic trends, so that if the atoms fall within the same group or in the same period, we can determine then which ones are going to be bigger based upon their position on the periodic table. And then we saw then that the sizes of the atoms increase as we go from right to left in a period, and from top to bottom in a group. So therefore then in the lowest left-hand corner, the lower left-hand corner, that's where we would find the larger atoms. Okay, so we saw that. And then we also were able to discuss these isoelectronic series. The isoelectronic series is a series of atoms that have the exact same number of electrons. They have the exact same electron configuration. And based on that, we can use that and determine the sizes of the atoms. And we saw in that case then, if all those atoms in isoelectronic series have the same number of electrons, we saw then the factor that determined then the size of the atom is going to be the number of protons. That is the atomic number of the atoms themselves. And so we saw then that when the atomic number increases, when we have an increase in the number of protons, the size of the atom actually gets smaller, which I think makes intuitive sense, because what we're doing then is, if we have the same number, if every atom in an isoelectronic series has the same number of electrons, the number of protons then will determine then how much those electrons are pulled in or how much they're allowed to spread out. And remember, the size of the atom then is going to be determined by the electrons. The closer the electrons are to the nucleus, the smaller the atom will be. The further away they are from the nucleus, the larger they will be. And so then you can, I think it makes sense then that if you have an atom with more protons, thus the atomic number will be larger. Those protons will pull in on the electrons more, thus making the atom smaller. So the conclusion, the final, what we were able to conclude with that then is that for an isoelectronic series, and only for an isoelectronic series, there is an inverse relationship between the atomic number and the size of the atom itself. So therefore, as the atomic number increases, the atom's size decreases. And again, I need to specify and I need to emphasize this, that that rule only holds for an isoelectronic series. And so make sure you keep that in mind, okay? All right. So with that said, then what we're going to do today is we're going to shift our attention then to examining more closely then why ionic bonds are stable, okay, and which ones are going to be stable, and we can calculate for the energy associated with that stability. So we're going to take a look at that. We're going to take a look then at how we can calculate for it. And so we're going to use a term here that you are familiar with. We've used this term, lattice energies. We introduced it to you last semester. This semester, we get a chance to study it a little bit more, and actually calculate for it as well. Okay. All right. So we know then that when two atoms get together, and when one atom's in metal and the other atom's in non-metal, you're going to get an electron transfer. Electron transfer then generates and creates one atom that is positively charged, your cation, another atom that's negatively charged, your anion. When those two get close to each other, the attraction between those two is going to form a bond that is the ionic bond, and in doing so, you lower the energy. We saw then with Coulomb's law that attractive force then is going to be fairly strong, and it will be dependent on the charges of the atoms and also how far they are away from one another. And we will see, and we will use a version of the Coulomb's law again in order to calculate for this lattice energy here that I've shown you here. Okay, so this lattice energy is the energy that is the way that we can determine then how strongly those ions are attracted to each other. And this lattice energy here is an energy that we can calculate. We can calculate for that energy. We can't actually measure this, so this is not an energy that we can measure. We actually get it indirectly through other energies that we can measure. Okay, and so we have to calculate for this lattice energy right here, and there's two ways that we can calculate for it, and we're going to go through both ways today. Okay, and so how we define this lattice energy then is the energy that is given off, when two ions find each other. Okay, two ions in the gas state find each other, and they form this solid here. So going back to what we talked about here, this is a cation, okay, and we, back in chapter 7, remember, we talked about ionization energy is the energy needed to remove an electron from an atom, a metal atom, in its gaseous state to form this gaseous cation here. This then is your electron affinity, and your anion, and that forms as a result of a nonmetal atom having a high electron affinity for electrons, drawing those electrons in, and thus forming this anion here, also in its gaseous state. These two atoms here are in the gas state very far apart. Remember, in the gaseous state, atoms are very far apart, and that's one of the key characteristics of a gas. And so therefore, even though it is favorable for them to be in this, even though that when we talked about the atoms should attract one another, that this is a positive, this is a negative, and it would be favorable for them to be attracted to one another, in the gaseous state, they are very far apart. So the distance between them is very far. It's very difficult for them to be attracted to one another. The way that you kind of imagine this is if you take two magnets, and hold the north and the south end of the magnets towards each other, but you hold them very far apart, you're not going to feel that force of attraction. So if they're very far apart, they will not be attracted to one another. So what will happen is, as you bring these oppositely charged atoms closer and closer and closer together, then what you're going to start seeing is that they will attract one another. At that point, then they're going to start moving on their own towards one another. And when they get close enough, they will form a matrix here, a solid matrix. And it's this formation, the formation of the solid form here, that creates the very strong interaction that accounts for example, the very high melting points and high boiling points of ionic solids. Okay, so you want to make sure you keep that in mind as you move forward. So the lattice energy then is the energy that is released when gaseous ions in the gaseous state, okay, come together and they start forming the solid, and so they are packed very closely together to form that ionic solid. And so if they're packed very closely together, the distance between them would be very small. And remembering back to Coulomb's law, R then would be very small. And if R is small, then the force of attraction will be very, very large. Okay. All right. So like I said, we can calculate for this lattice energy. And this lattice energy is going to be the energy, again, that's released, the energy that's being released as the two ions in its gas state form one another. But that lattice energy is only one of the energies that we need to form what's called to determine then what's called the overall energy of formation, okay, which is what we will eventually, I will introduce to you later, but I'll point it out to you now. We refer to that as the enthalpy, the change in enthalpy of formation. And this is what we call the standard enthalpy of formation. And we'll talk about what standard conditions are in chapter, and the energy chapter. So this is the standard state, okay, standard states and what they are. It's a little bit different from STP. So this is standard enthalpy. F here represents formation. Okay, so this is the energy of formation of an ionic compound. That energy of formation is made up of 5 different energies. Okay, the energy of sublimation, the ionization energy, okay, the energy of dissociation, the electron affinity, and there it is. There is your lattice energy. Okay, these 5 together, when you total them up, will be the energy of formation. Therefore, then, what we can do then is, in order to calculate or to get this lattice energy, we're going to use what's called the Born-Haber cycle in order to find this, and I'll show you that in just a moment. It sounds fairly technical, but the process is very straightforward and simple. Okay, all right. So these 5 energies together, when you add them up, will give you then the standard enthalpy of formation. And so this is what we refer to as the standard enthalpy of formation, or if you want to think about it, this is also known as the heat of formation. And you'll see both terms being used in the book as well as in other textbooks as well. Okay, so this is what we'll be calculating for. This can be measured. We can measure that. We can measure the ionization energy. We can measure the dissociation energy. We can measure electron affinity, and we can measure delta H standard of formation here. And so therefore, from that, then we can calculate for the lattice energy that we are given right there. Okay, all right. So let's go ahead then. Let's take a look at an example here. Let's look at the formation of lithium fluoride. Let's take a look at how lithium fluoride forms. In order to do that, what we're going to do is we're going to assume then 1 mole of lithium fluoride forming, and so therefore 1 mole of lithium solid forms with half a mole of fluorine in order to form lithium fluoride. Okay, so let's go ahead and let's take a look at some of these energies here. Okay, so we can go ahead and we can measure then the very first one here. So the way you want to think about this process, the way you want to think about how lithium fluoride forms, that you have to first take lithium solid and you have to basically evaporate, turn it into a gas without going to the solid. So that is, remember, what we refer to as sublimation, the process by which a solid becomes a gas without going through the liquid state. That's the process of sublimation. This is the energy associated with sublimation. So we'll call this the enthalpy of sublimation. Okay. and that's equal to 161 kilojoules. And this will be kilojoules per mole, remember. So kilojoules per mole, so this is going to be 161 kilojoules per mole. If you notice then this is a positive 161, meaning then that this is going to be an endothermic process, meaning that whenever it's positive, means then that you have then energy that has to be absorbed. Energy has to be put into the system in order to get that done, which means that, which makes sense, energy is required to essentially separate out the solid ion atoms here to form the gaseous atoms. Now understand, we're not forming the ion here yet. We're just going from the solid to the gaseous state. Imagine this. I think you can relate this also to melting, for example. When you melt ice, you have to heat up ice. You have to put energy into ice in order to melt it from the to get it from the solid state to the liquid state. Okay, so that's the first energy right there. That's the energy of sublimation. Okay, then the second one, then you have to ionize. Once you have your atom, in the neutral atom in the gas state, in order to form the compound here, you got to make sure then the lithium, the cation, is formed, and that means that you have to remove an electron. And that removal of an electron is what we refer to as the ionization energy. That ionization energy, you have to ionize it. So we can basically call this also the enthalpy of ionization. And again, if you notice then this is also positive. So therefore this is also endothermic, which means then this requires energy to be put in to remove that electron right here, which makes sense again because that electron wants to stay close to the 3 protons here in lithium, so it's going to require energy to pull that electron out. So that's also a positive value here. Okay, all right. What we have next here then is what we refer to as the dissociation energy, which we will talk about hopefully next week when we focus on covalent bonds. Okay, but that is essentially the energy needed to break the single bond between the 2 fluorine atoms. Okay, so this is going to be the enthalpy of dissociation. That means the heat energy needed to dissociate. This is a positive value, kilojoules per mole again, which means then that this is endothermic. And what does that mean for us? We have to put in energy to break this single bond here between the 2 fluorines, which makes sense again because that bond then is what causes this molecule to be stable. And because it's stable, it doesn't want to change. We have to then energize it. We have to put in energy to break that bond to form a fluorine atom here. Okay, all right. All right, so the next energy then that we're going to take a look at then is this is the energy that's needed for a single fluorine atom to attract an electron. Okay, so this is your electron affinity. Okay, and that's energy that's needed. That's energy that's associated with bringing the electrons in. Now, if you notice here, okay, and I'll call this EA for electron affinity, this is negative. This is a negative value, which means that this is an exothermic process, meaning the energy is being given off. The fluorine here, remember, wants that extra electron. The reason why it formed this bond in the first place is fluorines, remember, are deficient of 1 electron, and once it gets that 1 electron, it has its octet. So this fluorine atom here with only 7 electrons, this is neutral fluorine, wants this electron. It wants to pick up that electron to form this fluoride ion. And so because it does so, it will give off energy. So whenever you have an exothermic process, we'll learn this when we get to the energy chapter, this is a favorable process. It can happen spontaneously. Okay? And so there it is. There's your first energy releasing event. So far up here, we've had energy absorbing events. This is our first energy release event. Okay? All right, so at this point then, we have our fluoride ion and we have our lithium ion together. Okay, so we have, but both of these are in the gaseous state. And remember, as gases, they are very far apart. They want to be attracted to one another, but they're too far apart to be attracted to one another. And so this last energy here, this is your lattice energy. Okay, and as a result then, when these two get together, a whole lot of energy is going to be given off because they want to be attracted to each other. And so this energy here, this lattice energy here, if you notice, is also exothermic, okay? Which means then as these 2 ions find each other, okay, they give off a lot of energy. Okay? All right, so there are the 5 energies that that I mentioned in the previous slide. Okay? And so when you add all these energies up, when you add all these energies together, okay, when you add all these energies together, when you add up the left side here, you can end up with this overall equation here. Okay? And if you notice, if you do the math there, you will cancel out um, these atoms here. For example, fluorine, you got fluorine gas here, you got fluoride, I'm sorry, the fluoride ion there, I'm sorry, the fluoride ion here, okay. Lithium gas here, and so we end up then with the lithium solid on this side, okay. You have the half of the fluorine gas on this side, and you have the lithium fluoride on this side. So all that adds up, okay, so you're basically adding up everything on the left here. And so you add up everything on the right here, and then this is the amount of energy that's needed. If that's in, when you total up, that's the energy that's left over. And if you notice, the overall process is exothermic as well, which means then that the formation of lithium fluoride is a favorable process. It's something that is going to happen if you can get it to go, and it's going to be spontaneous because this is an exothermic process. Okay? All right. So positive energy then means that the process is endothermic. It means that energy is required. Okay, positive energy means energy is required. Endothermic. Negative energy means that the process is exothermic. It releases energy. So this is absorption of energy. Okay, that's endothermic, and this is the release of energy, exothermic. Okay, so the next slide here then shows us then what happens here. I think this is a kind of a good way to kind of visualize what's happening here. So this is the starting point that we have right here. You have here a solid lithium and fluorine gas, 161 kilojoules here. This is to take the sublimation energy, take the liquid, solid lithium to gaseous lithium. The 520 kilojoules of energy is to take this lithium atom to form the ion. This is your ionization energy. So this is your sublimation here. This very first step is sublimation. So as you notice then, we are adding energy. We're moving up in energy here. This is ionization energy, which means then at this point then, we are investing energy and not getting anything back. Ionization, sorry guys. So you can imagine then that we're investing energy here. We're investing 161 kilojoules of energy here. We're investing another 520 kilojoules of energy here. And so to form the lithium ion, here then we're investing 77 kilojoules of energy in order for us to form this atom here. And so up until this point then, we've been investing, and not getting anything back in our return. And so the very first step here then, when fluorine becomes the fluoride ion, we get our first negative, our first return there. Okay? So we want to be able to get an overall return on our investment. And so if you notice here, when these two, at this point here, we get the lithium ion and the fluoride ion, when they find each other and they form the lithium solid, we get this huge return on energy here. And so therefore then, the overall change that occurs from start to finish here is negative 617. This again is what's known as our enthalpy of formation. Okay? That's your enthalpy of formation. That is then designated then as delta H, F, and it's under standard, so we call that the standard enthalpy of formation, and that's the amount of energy, the overall amount of energy needed to form the lithium fluoride compound. Okay, and remember, this is the solid. This is a lithium fluoride ion in the solid state. Okay, all right. And so with that said, then we can calculate, and if you notice here, we can calculate for that energy if we know the charges of the ions. Okay, this remembers the Coulomb constant, and this is the distance between the two ions. And so this proportionality constant is very similar to what we saw with the Coulomb's law, calculating for the energy of the Coulomb's law. So we can calculate for this lattice energy in this particular manner here, as long as we know the charges, the magnitude of those charges, and if we got K, R here is the distance between them, we would have to be able to measure that. We can calculate for this lattice energy. Okay. All right. But these are fairly difficult numbers to come across. Okay? They're fairly difficult numbers to come across. And so what we're going to do then instead then is we're going to take a look at a method in which we can calculate for the lattice energies using energies that we can measure, much more accessible. But before we get to that, I just want to make sure you understand then that if we take a look at a solid compound, like for example, a solid lithium fluoride, okay, the reason why the lithium fluoride is so stable, and we saw this again, is because the lithium ions and the fluoride ions, remember, when they're far apart, they have a hard time finding each other. But when they find each other, they form this very stable structure here, okay? And if you look at the atomic structure here, you have an alternating pattern of fluoride ions and lithium ions. And the reason for that is you have the negative charges here being attracted to the positive charge, and this extends through the whole system here, okay? So you have many positive charges, many negative charges attracted to one another, and that is that's what creates this very stable structure. And that's why lithium fluoride is a very stable solid, very high melting point, very high boiling point, because if you have this alternating pattern here that allows the atoms, these ions, to get very close to one another, and also to share charges. Okay, so if you can imagine then here, you have the cation being surrounded by 1, 2, 3, 4 anions right there. Okay, so you have a very stable structure. Okay. All right. So essentially, what happens is in the solid structure, we are able to maximize the attractive forces and minimize the repulsive forces between these ions here. Okay. This structure here, this structure is a fairly common structure. Okay, and we call this the sodium chloride structure. And we just name it that way is because sodium chloride is the most common ionic compound that we have, and it also has the same structure as well. So this is the sodium chloride structure for this particular compound. Okay. All right. With that said, then what I'm going to do then is I'm going to stop right here. And I'm going to assume then that we're going to have a shortened period. Again, I'll let you know on Monday. And on Monday, what we'll do then is we'll pick up with with this discussion here. We'll talk about the Born-Haber cycle and how we do that calculation. And so today, folks, nothing that you need to turn in. I'm sorry, I'll assign a couple problems for you to do in just a moment, but nothing that we've done. No, we haven't done any of the problems during the course of the lecture. So I'll assign a couple problems for you to do to give you some idea of what this lattice energy is, and give you a chance to practice that, and then you'll just turn that in, okay? All right, so have a good weekend, folks, and I will hopefully see you after school today, and if not, then I will see you on Monday, okay? All right, I'll talk to you folks then.